Thank you, Simon. So,
no mic.
There's mute button on the top.
So today I'm going to talk about how to write nested data parallel programs, compile them, and execute them directly on the GPU efficiently. This is joint work with my advisor, John Reppy, at the University of Chicago. So GPUs provide a lot of parallelism, but they've done it by making a trade-off in how they use the silicon. They've taken away all of the wonderful things that we love, like a lot of big multi-level caches that make it easy to write code that has non-uniform access patterns, and traded it off for a lot of parallel hardware. But the problem is, this shifts the burden to the programmer. Now, in order to use all of that parallel hardware, well, you have to write your code with full awareness of how this architecture is laid out. And so for regular programs, programs where the shape of the data is pretty regular and predictable, where the operations that you're performing on each of the elements of those arrays are pretty predictable, there are some great libraries and languages available for you. The CUDA and OpenCL extensions of C and C++ have been used by a lot of people to write very high-performance programs, and the libraries are pretty mature at this point. BLAS provides you matrix and vector operations. Thrust gives you reduce and sum, and a lot of the other operations you expect to have. And just about every respectable high-level language has 2 to 3 implementations of these flat data parallel primitives. So it's merely extremely difficult to write something like matrix-matrix multiplication, but you can do it with just a lot of time. Now, irregular programs, on the other hand, things that don't operate uniformly over the data or that have unpredictable data structures, now that's serious work. You're going to have to take a graduate student, teach them to program for GPUs, send them off for a couple of months, budget for Alcoholics Anonymous afterwards. But on the other hand, you do get a paper out of it. There's usually so much that you learn about the hardware, new tricks for how to represent all of these very complicated algorithms like traversing a tree, that you can get a paper out and you can talk about it and really advance the state of the art. And I think that's fine for places like high-performance computing, where you expect people to try and get every last erg out of the hardware. But it'd be nice as programming languages people for us to have some model to automatically take these programs and run them efficiently on GPUs. And fortunately, we do. The nested data parallel programming model has been around for a long time, and it extends the flat data parallel programming model to support irregular parallel programs. And what we've based our work on is the Nestle work by Blaylock that was done in the early 90s, targeting wide vector hardware like crays. And basically the way that it works is this whole program transformation that changes the representation of all of the data and then all of the corresponding control constructs back into one of these flat data parallel programs. So let's walk through an example of how it works for a pretty simple program. Sparse matrix vector multiplication. So this takes a sparse matrix A and a vector X, and for each row in parallel, it computes the sum of, in parallel, all of the elements that are present in the sparse matrix, along with their corresponding element from the vector. And so there's lots of nice nested parallelism in there. And the representation of the sparse matrix even sort of makes sense. It's a vector of vectors where each of the elements is a tuple of the column, of the corresponding column and the data value. And so we can see that, and as functional programmers, that seems sort of reasonable. And as a GPU programmer, that looks horrible, because there's just no way to, you can't at runtime figure out, how am I going to chunk this up? What's the right thread block size for these? How am I going to partition this data so that it'll run well on the GPU and be nice and uniform? So in practice, what you do is you give up and you throw this code out and you write a completely different version of it. Now these completely different versions are quite a bit larger. In this bar chart, I show the Nestle program on the left, and on the right bar for each one, I show the corresponding CUDA program. These CUDA programs are the best hand-tuned optimizations of the corresponding algorithms that I can find. They aren't just sort of me hacking up a quick version of Black-Scholes in CUDA in an afternoon. So there's about a factor of 10 difference. Now I've got a star next to convex hull because the best algorithm there actually supports more higher dimensional cases. So that's not totally fair, but I bet if they only supported the 2D case, they would also be a factor of 10 larger. So how does this transformation actually work? How do we stick with these nice short programs? Well, first we transform all of the data. So we take that sparse matrix that we had before, and we untuple all of the elements. So now you've got two flat vectors, one that has all of the column indices, and that's the top flat vector there, and one that has all of our data values. And then we introduce a third vector called the segment descriptor. And what this has is all of the length information required to reconstruct the original irregular data structure from before. And that's the piece of data that we use in all of the primitives later, where we were doing something that only operated on one segment of the data, so that it knows which segment each of these now flat values are in. Because, we can't just pass the colors along. Now, the control flow is also transformed. I'm not going to talk in detail about how that happens, because that's a long discussion. But I will go through how this executes on the processor. So I've added a vector here whose elements are just the floating point values corresponding to their indices to make the math nice and easy. And so, if you remember, the inner parallel step was to multiply all of the values that were present in the sparse matrix with their corresponding element in the flat vector. And so that's really easy to do. Even for GPU programmers, we can do this easily, possibly even for multiple GPU cards at the same time. You just chunk it up evenly into whatever block size fits. And then after that, we had the parallel sums that we had to perform. And that's a little bit trickier, but there was some great work in 2007 by Sengupta and Harris showing how to perform segmented sums efficiently on the GPU. So we can still make really good use of the card by just taking that intermediate result along with our segment descriptor and then packing it all down. So, great, we've solved the problem, right? Just spend a graduate student year or so porting the back end of Nestle and then it all works. Well, that would be nice, except not quite. Crays and GPUs are slightly different pieces of hardware. So we had to extend the tool chain a bit. So the blocks that are shown in blue here are the pieces that we added to the pipeline. Basically, we start out with any of the default Nestle programs, and I'd like to emphasize that you can take any of the benchmarks off of the Nestle side, any Nestle code you've written in the last 20 years, and pass it through our compiler and run it on the GPU. And then we pass it, that generates a stack-based intermediate representation. Now, unfortunately, that's not terribly efficient by default, so we pass it through our optimizer, which generates a CUDA file. We then hand off to the CUDA compiler to produce some nice, more optimized code, and our interpreter and set of associated runtime library calls. So probably the most important optimization is fusion in this case. So taking this nested data parallel program, MOLAD, which just takes in 3 vectors, multiplies 2 of them together, and then adds in the third. If we pass it through the Nestle compiler and then remove some of the redundant operations, we end up with some stack code that looks like this. Now, there are 2 big problems with this code. The first one is that there are 2 separate GPU calls. The call to a parallel element-wise multiplication and an element-wise addition. Each GPU call introduces some additional latency, and in total, if you have MOLAD in an inner loop, that's going to really kill your performance. But the much bigger problem is that after the element-wise multiplication, we store the result back into global memory on the GPU, and then we call the addition operation, which then pulls it back out of global memory on the GPU. And if you remember all the way back from slide 2, that cache is gone. We don't have it anymore. So these are nice, slow, unless you get extremely lucky and the scheduler all plays nicely with you. But most of the time you don't, because it's a GPU. So you have terrible performance. So what we do in this case is instead we produce a fused kernel. So in one call, we go ahead and we remove the extra allocation and the extra writes and reads from global memory by just producing some line noise down there. On the library side, the biggest piece that affected our performance was the representation of the segment descriptor. If you remember from earlier, I said that these segment descriptors that we produce are the things that are used by all of the library functions to figure out where the boundaries are between these segments, and for each of the elements in your vector to know, I'm at element 33, which actual segment am I in? And this is very important for all of the operations like extraction and permutation, because this programming model likes to shuffle vectors around to make them run well on the live vector hardware. Now the problem with this, or the CPU model, which just has lengths here, works really well because we have a lot of caches. So if you have a 1,000,000 element vector and each of them goes to figure out what their offset in the segment descriptor is, it doesn't matter because that segment descriptor is held nicely in cache. But when you're on a GPU, that's absolutely terrible. You end up spending a long time. If you have 1,000 elements on the GPU all reading through the same segment descriptor, you can almost watch them do it. So instead what we do is we pad out the segment descriptor up to the length of the vector with the corresponding segment IDs. And this is a huge memory trade-off that we've decided to make because you end up having to do it anyway on every GPU call, so we might as well do it up front and hold it along with us. And then for extraction and permutation, that's all we need to be able to perform those operations quickly. Now for segmented scan, it's a little bit different. We also still needed the lengths, so I decided to tack those on the end because while you can compute them dynamically at the times that you actually run into segmented scan operations, it turned out to be more efficient to just compute them beforehand and have them carried around. So we've benchmarked on 5 different platforms here. The first one was an extension of Python called Copperhead. Now Copperhead provides flat data parallelism. It's like most of the GPU language embeddings. And so there are a bunch of examples, and this is work that's being done at NVIDIA right now. The data parallel Haskell project, we've decided to include even though it targets CPUs because they're sort of the modern successor to all of this work on flattening of higher order programs. The CUDA programs, as I mentioned before, are the highest performance CUDA programs that we could find out there. So I went around and talked to all of the authors of papers, and the ones who weren't too embarrassed by their code handed it over. And then finally, we have 2 versions of the Nestle programs. One is on CPUs, so our CPU backend is only serial, but it does perform a bunch of loop unrolling and vectorization, so the performance isn't abysmal. And we have a GPU version and the GPU version as well. So the first benchmark is just a flat benchmark, just to see, how much are you paying for getting to use a nice declarative language. And so if you look, our Nestle GPU numbers are shown in red here, and the CUDA numbers are shown in green. And so you pay about a factor of 5 slowdown, which isn't terrible for, over the Kubla's highly tuned and carefully implemented version of all of these operations. So we think that it's not a huge penalty to pay for using this library. Convex hull is a benchmark that finds the convex hull of a set of points in the 2D plane. And in this case, we're actually within just a couple percent of the best known performing implementation of GPU-based convex hull provided to us by the National University of Singapore. So this is one of the examples where our optimizer and the problem domain fit very well together and we managed to produce a great program. Now you'll notice that at lower problem sizes, the CPU just wins all the time. But that's the GPU, which is like driving a car to go next door for small problem sizes. It's usually not worth it. Now finally, here's a benchmark where we don't do well at all. Barnes-Hut, the hierarchical n-body problem. And so there's the version that we have here, shown in green, was provided by Pingali's group. And it's a great, wonderful implementation, nearly 2 orders of magnitude faster than us. And our problem here is that we haven't finished the optimizer. There are still, for instance, many of the optimizations provided in data parallel Haskell, such as MapReduce Fusion and some of the size analysis, are not implemented yet inside of Nestle GPU. So we believe there's a lot of low-hanging fruit to help close this gap, but I want to set expectations appropriately. It's not going to beat the best tuned, it's not going to be highly competitive with the best hand-tuned GPU code for every program that you throw at it. But it is better than, some C programs. So the related work in the data parallelism space, it really started out with the Parallelation Disk project by Blaylock and Sabot, but we based our work on Blaylock's Nestle project, as I've mentioned several times through this talk. Now, one particular piece of work that came out of that project was Chatterjee's PhD work, where he was targeting MIMD architectures, and he had to do something very similar, produce a custom optimizer, perform a lot of size analysis to provide a different to much more highly optimize the code for that particular target architecture. Now, Palmer and Prinz worked on the Proteus project, which is another interesting implementation of flattening, because they didn't require that, they still flattened all of the vectors, but they didn't require that the vectors were contiguous blocks. They could actually have them chunked or hierarchical, which would be nice for, when you compare a GPU to our modern CPUs, they have relatively limited amounts of memory. And so one of the limitations that we run into right now is that, if you need more than 4 gigabytes of space for your data, you're just sort of out of luck right now. And of course, the work by Keller and Chakravarti has really taken all of the work on flattening and moved it forward in the context of Nepal and data parallel Haskell, because Nestle is a wonderful declarative language, but it's still first order. So their work extended the flattening transformation to higher order, recursive data types, all of the things that you expect when you sit in a conference hall at a conference like this. So in conclusion, we believe that flattening is an effective approach for GPUs. I would love to see a whole bunch of different, instead of more embeddings of flat GPU languages inside of languages, I would love to see people transforming languages so that you can have more interesting algorithms in them. And the Nestle GPU compiler and libraries are already useful and fairly competitive. I encourage you to just throw programs at them and see how they perform, especially if you're thinking about subjecting your graduate students to writing GPU code with CUDA. But there are still a bunch of optimization opportunities here. Size analysis and fusion and macro use chains are the two big ones. Thanks for your time.